Welcome to Spring LIB.
In this problem on the topic of oscillators, we have to imagine that a small circular hole is drilled all the way through the center of the Earth, and we drop an apple into this hole at one end. We want to first show that if the Earth has a constant density, then the motion of the apple will be simple harmonic, and we want to calculate how long it will take the apple to return. We can ignore all frictional effects in this problem. Now, at points within a solid sphere, say 100 kilometers below the Earth's surface, only the mass up to that radius contributes to the net force. The outer shells beyond the point in question contribute zero net gravitational effect. So when the mass is a distance r from the center of the Earth, there will be a force toward the center opposite to r due only to the mass within the sphere of radius r. We call that mass mr. It is the density of the Earth times the volume within a sphere of radius r. So mr is equal to the density of the sphere rho times the volume of that radius vr. And so we can write this as the density of the Earth, which is the mass of the Earth me divided by the Earth's volume ve times the volume vr. And so we could write this as the mass of the Earth me divided by 4/3 pi re cubed, where re is the radius of the Earth, and we assume that Earth is spherical, multiplied by 4/3 pi little r cubed. So we can see that this simplifies to the mass of the Earth me times the point r cubed over the radius of the Earth cubed. And we also know that the force from Newton's law of gravitation is g, the universal gravitational constant, times the mass of the object times the mass at radius r divided by r squared. And so this is equal to minus g times m times the mass of the Earth, me, the mass of the Earth, we'll use capital M, me, times r cubed over the radius of the Earth cubed, and this is all divided by little r squared. And so again, we can simplify this force, and this becomes minus g m times the mass of the Earth, me, over the radius of the Earth cubed, all multiplied by little r. Now the force on the object is opposite to and proportional to the displacement, and so will execute simple harmonic motion. With a spring constant, or an effective spring constant, k, and k is equal to g m me divided by re cubed. Now the time for the apple to return is the period, and we can use the spring constant to find this period. And so the period using the effective spring constant t is 2 pi times the square root of m over k. And so if we open out this equation, this becomes 2 pi times the square root of m divided by g m me over re cubed, which is 2 pi times the square root of the radius of the Earth cubed divided by the gravitational constant g, times the mass of the Earth, me. Now, if we substitute our values into this equation, we get this to be 2 pi times the square root, and the radius of the Earth is 6.38 times 10 to the power 6 meters, or cubed, divided by the universal gravitational constant 6.67 times 10 to the minus 11 Newton meter squared per kg squared, multiplied by the mass of the Earth, which we know to be 5.98 times 10 to the power 24 kg. And so computing this, we get this period, or the time taken for the apple to return, to be 507 seconds, or 84.5 minutes.